is E&M section 3.4.4, the electric field of a dipole. So far we have only talked in the context of dipoles or multipoles in the context of the potential. So we have written the dipole potential as something that depends on how far away I am from my dipole and an angle of orientation. Okay, we can discuss more about that. That being 1 over 4 pi epsilon naught, the direction that my dipole, or that I'm looking to evaluate my field, dotted with my dipole moment over the distance that I am away. Okay. So in general, I have some dipole that's pointed in some direction, has some moment, and I want to evaluate my field at some point. So I have this vector that points from the center of my dipole to the point I want to evaluate my field at. Okay. This is going to be a whole lot easier to discuss if we put our dipole at a particular point in space, oriented in a particular way. All right, and you might guess what that point is. It's the origin. So let's go ahead and pick the origin as the location of our dipole. And I'm going to change or define the orientation of my dipole, or the orientation of my coordinate system, if you prefer that, to match. So the dipole is now pointed along the z direction. There you go. So that makes it a lot easier for us to go ahead and define an electric field, because I know that the electric field is the negative gradient of my potential, and because my dipole is now aligned with the z-axis, this dot product here is going to be a lot easier to deal with. Okay, so let's go ahead and write what that dot product is. It is 1 over 4 pi epsilon naught r squared. Okay, and now if I have some random point in space that I care about to evaluate in the field at, this vector here is r, and the angle between these is just our polar angle that we've defined via spherical coordinates. So that is going to be the magnitude of p times cosine theta. All right, so to do this gradient, we have to do this in spherical coordinates. So that is minus the derivative with respect to r in the r hat direction, plus 1 over r, derivative of our potential, with respect to theta and the theta hat, plus 1 over r sine theta, derivative with respect to phi and the phi hat of our dipole. All right. So that first term there gives me a 2p cos theta over 4 pi epsilon naught 1 over r cubed. That's the r hat direction. That second term gives me a p sine theta over 4 pi epsilon naught r cubed, and the theta hat direction, and there's no phi hat direction, so that gives me 0 in the phi hat. I can pull out some things that are constant and say that the electric field of my dipole is something that depends on the distance that I am away and the orientation between my observation vector and my dipole moment. That is equal to the magnitude of that dipole moment over 4 pi epsilon naught r cubed times 2 cosine theta in the r hat direction plus sine theta in the theta hat direction. All right, so let's sketch what that looks like. I'll do this in the xy, this is the zy plane. Y, z. I have my dipole pointed upwards. And let's go ahead and investigate what a couple different regions of space look like. So I'll do point up here, here, and here. Okay, and let's assume that we're at the same distance away on all those points. And I want to know what direction is E pointing at those regions of space. Okay, so I'll call this 1, 2, and 3. E1, okay. E1 is going to be, I mean, all of these are going to depend on what the polar angle is, theta. Okay, so theta for this is going to be equal to 0 because I'm along the z-axis. So then my electric field at point 1 is going to be something related to the r hat direction, because cosine of theta is equal to 1, or cosine of 0 is equal to 1, plus, well, sine of theta is equal to, sine of 0 is equal to 0, so there's no theta hat component, and everything is pointed in the r hat direction. Okay, r hat direction at this point is up. All right, what about point 2? Theta here is now pi over 2. We see that the pi over 2 is going to kill the cosine, so that means that I'm only left with something that's in the theta hat direction. What direction is the theta hat pointing, right? At every point in our Cartesian coordinates, theta hat points in different directions, but on the y-axis, theta hat is pointed down in the minus z. All right. Theta here is going to be equal to pi. All right. Pi will mean that I have cosine of pi is going to be minus 1, so something in the minus r hat direction, and nothing in the theta hat direction. Okay, well, at this point in space, the r hat points outwards, and minus r hat points inwards. So it's pointed like that. Okay, so I can draw my field lines connecting those. Right. And this is the field of a dipole. Looks like this.